back to the course on nanotechnology applications in agriculture. So, in this module exclusively we will be talking about the nanomaterial synthesis, nanomaterial classification and the characterization tools which are being employed. So, as you have already aware, in the previous class we talked about the classification of nanomaterials, okay, and in that, just to have a brief recap what we talked about the shape and geometry based on which the nanoparticles are being classified. We talked about the chemical nature based on which they are being classified, and we talked about nano cages, nanocrystals, nanobelts, nanofiber, nanoparticles, nanotubes, nanowires, quantum dots and nanocomposites, and I gave exclusive examples highlighting how each one of these could be helpful. And one thing which I missed out, that many of these structures are exceptionally helpful in developing next generation of biosensors for agricultural applications, because when we talk about precision farming, where we are talking about based on the soil assay, how precisely we have to apply the fertilizer in order to ensure a sustainable growth of the ecosystem, then we need to test, we need to have small sensors or micro sensors which could be used or utilized to detect the different contaminants in the soil. So, one of the areas where tremendous amount of stress has been put in precision farming is developing nano-based sensors for agricultural applications. So, the next classification route what we have discussed was the chemical nature, where we talked about the organic, inorganic and carbon based. And in the organic we talked about dendrimers, micelles, liposomes, ferritin, and most of them are biodegradable and non-toxic, and most of them have hollow cores, and they could be used as nanocapsules to deliver any kind of active ingredient or any kind of agrochemicals at a specific site. Not only that, much of these organic nanocapsules could be tailor-made to open up or close according to the electromagnetic radiation or any other form of radiation like heat or some other source of energy. Okay. Similarly, in the same line we have the inorganic nanomaterials, which are mostly either aluminum, cadmium, cobalt, copper, silver, gold, iron, zinc, lead. So, most of these metal based are also used to deliver different forms of pesticides, or they could even at times could replace the pesticide in order to reduce the requirements of pesticides. So, we have talked about these different forms of inorganic ones. We talked about the metal sulfide, rare earth and metal oxide based ones, and then we talked about the carbon based one, where we highlighted about fullerenes, graphenes, carbon nanotubes, carbon nanofibers, carbon dots, activated carbon, nanodiamonds and all these kind of other structures. So, today what we will do, we will pick up this part where we talk about broadly about the synthesis of nanomaterials. Let us start the synthesis of nanomaterials. So, in terms of the synthesis, when we talk about, there are three broad classification of synthesis. Either it will be a physical synthesis, or it will be a chemical synthesis, or it will be a biological synthesis. Now, there may be time where we may be using two different techniques. Maybe we will be using physical and chemical, physico-chemical method of synthesis, or chemico-biological methods of synthesis, or biophysical methods of synthesis. So, or maybe we may use all the three: physico, chemico, biological route of synthesis. As more and more nanotechnology is advancing, these watertight compartments of synthesis of nanomaterial is slowly kind of, the gap or the clear cut demarcation is slowly getting removed. They are almost now merging. But what is interesting to note here is that all these synthesis falls under two different approach, whether it is a top down approach or it is a bottom up approach. Okay, so when we talk about a top down approach, so basic classification, they could be classified into two groups. Start different methods of synthesis of nanomaterials. Okay, so either it will be a top down approach or it will be a bottom up approach. When we talk about a top down approach, so essentially what we are talking about is we take a bulk material, something like this. This is a bulk material, so which is filled with atoms which are constituting this bulk material. Now this bulk material has exposed surface area like this. This is the exposed surface area you could see. Now what we do is we take this bulk material and we break it down into, say, powder. So what we are getting is something like this. They could be uniform, or you can categorize them. You can fine tune them. You can filter them, something like this, depending on how precise or how precision filters you are having. And based on that, something like this. Okay, so depending on how finer you go, you decide the size of the nanomaterial. Say for example, if each one of these circles represents a single atom, then we are talking about a single atom out here. You're talking about 2 atoms, we are talking about 3 atoms, you can 4, like 5. Okay, so now if you look at it, the amount of surface which are available is, for that particular volume, is this much. So if you realize, as you are increasing the number of atoms, your per unit surface to volume ratio is decreasing, and if you are reducing the number of atoms, your per unit surface to volume ratio is increasing. So the reactivity of, so if you look at it, as we go down with the size, the reactivity is increasing in this order, and the exposed surface area out here on the other side is decreasing like this. So which is surface to volume. okay, whereas out here it is the reactivity which is increasing. So this is a top-down approach where you take a bulk material, grind it by different techniques and bring it to the atomic resolution. Whereas on the other hand, if you follow a bottom-up approach, what you do here is you are already having small moieties like this in the form of salts, in the form of gels and whatsoever. Now using, so you're having the atoms and the molecules at your disposal. You either some form of self assembly, either it may be template based or natural self assembly or template based self assembly or chemical self assembly. There are multiple routes what you can follow here, by virtue of which you are creating specific structures. Say you create a structure like this, what we talked about, nano ribbons, okay, or you create a structure like this, what we talked about, cubes, like ribbon like structure. You can create particles like this. You can have different kind of dimension, different kind of shapes like this, okay. So this is the other approach where from small components you can confine them. So the way you do it is you confine these particles, you are allowing them to react. While they are reacting, you add some kind of agents in between which will give them something, some kind of a capping agent, what we call about, which will give them some form of assistance to self-assemble in a certain way. So depending on the type of capping agent which is used in a very small concentration as compared to the amount of nanoparticles, they are used in a very small concentration, but they help to separate out the particles in a way that, suppose it is there, so once you introduce the capping agent out here, they will help to separate out these particles in a certain way, and it may be possible you may receive something like this, something like this, depending on what kind of capping agent you are using. And as a matter of fact, based on the capping agent, in a synthesis where all the parameters are kept constant, just by addition of different kind of capping agent, you can vary the geometry of the particle very extensively. Fairly extensively you can change the whole geometry of the particle, because the capping agent is just like, not only it separates out the atom, it creates a finite distance between the atoms, and it creates a certain kind of unique bond dynamics between the atoms. So this is essentially a bottom-up approach of synthesis of nanoparticle. So where you reach here, which is, or here, same way, or you reach like this out here, you reach out here. So these are the two broad ways, and under these two broad ways, the top down and bottom up approach, what you are having are the broad classification nanoparticle synthesis, which is your physical, methods, chemical methods, and biological methods. So when you talk about physical methods, so what we are essentially talk about is we are creating mechanical pressure or high energy radiation or thermal energy or electrical energy. These are the different routes we are following, or these are the different forces which are employing, and what they essentially do, these different forces, they causes material abrasion, one aspect, they may cause melting, evaporation because of these physical forces, or they may even cause condensation. And this is how we generate nanostructures. So what you are getting is, and this physical technique is mostly, I won't say completely, but mostly employed for, if you look back to the previous slide we are talking about, mostly employed for top down approach, but that's not the complete fact. There may be a situation they could be used, that these physical forces could be used for this kind of self-assembly process also. They assist in self-assembly, but mostly if we look at it, the kind of physical forces we are talking about here are mechanical, pressure, high energy radiation, thermal energy, electrical energy, all could be used for both. So all these forces, so in other words, when the physical forces are used for bottom up approach, in that case that will cause, these may cause in that situation self assembly also. When we are talking about bottom up approach, self assembly leading to the formation of nanostructure. So this is where we are talking about bottom up approach, and this is where we are talking about these kind of things happen in top down approach. Okay, so now what are the different physical tools which are, so this is how the process works. Either there will be a mechanical pressure, there will be high energy radiation, or there will be thermal energy, or there will be electric energy, or even this could use magnetic field. Okay, it is possible that you can use magnetic field, or the part of energy could be utilized to either self assemble or bringing about some of these top down approaches. Okay, now what are the different physical techniques? So this is the whole basis how it happens. Now let's talk about the techniques, physical techniques which are available. So one of the major technique is high energy ball milling. Okay, high energy ball milling. So when you talk about high energy ball milling, so it's basically, say for example, suppose you have two balls like this and they are moving in different directions. Okay, so this is where you are allowing your material, to grind. You can control the speed of this. Suppose this is a material, something like this. Okay. You can control the speed of these spheres, you can control the size, you can control the contact area between them. So you can do a lot of manipulation, but this is something like an high energy ball milling. We'll talk later about the pictures of this, how it really works. Let's enumerate at this time what are the different techniques which are being used. Okay. Next in the line is pulse vapor deposition. We'll talk later about the detail of this technique. Okay, pulse vapor deposition. The one point you will realize in most of these physical techniques, they are pretty cost intensive technique. The third one is laser pyrolysis. You're pyrolyzing something using laser energy. Then you have flash spray pyrolysis, followed by electrospraying, then you have melt mixing. So at this point we are just enumerating all the different techniques which are available for physical mode of generating nanomaterials, and then we will talk individually about these techniques, what they signify and how these could be used, and what are the costs involved in it, and what are the different kind of nanomaterials which may require this kind of pretty abrasive and pretty cost intensive techniques, and all of them are fairly cost intensive techniques. Okay.